Today we'll start with the FSM. Okay, FSM Finite State Machine. That is Mealy and More machine. Okay. So what is this Mealy and More machine? We'll see. So we already seen the FSM in the previous circuits. Can you guess what is the FSM we seen? Mealy and More machine. Synchronous sequential circuits. We already seen synchronous sequential circuits. Synchronous sequential circuits are also like FSM, but they don't have any inputs. Okay, they don't have the any inputs. That is also an FSM. Okay, so what is FSM? FSM is nothing but finite state machine. Finite state machine. Okay, finite state machine. Okay, and this is nothing but we can call this as a synchronous sequential circuit. Synchronous sequential circuit with finite states, with finite number of states. Okay, finite states. Okay, there are two types are there in FSM. So one is Mealy and next one is More. Mealy machine and More machine. Okay, so first we'll see what is this Mealy machine. Mealy machine. So Mealy machine. Uh, Mealy machine. The output, whatever the output is there, output is function of the present input as well as present state. Present input and present state. Output is a function of present input and present state. So if you draw the circuit diagram for Mealy machine, so you have next state combinational circuit. This is the next state combinational circuit, and next you have state register. You have a state register. This is a state register, and next you have output combinational circuit. Output combinational circuit. Output combinational circuit, and here you have the inputs. Here you have the inputs, and the input is connected to output combinational circuit, and next here this will be feedback, and this is given to the input. Okay, and there is a clock will be given for the state register. Okay, so clock will be given for this one. Okay, so that means here output we can say that output is a function of what, present inputs as well as present state. Okay, so if you see the state diagram, how it will look like means you have let us take two states are there. This is state one state, and this is other state. Okay, so this is the start of the start state, and so here this is input by output. Input by output. Did you understood this? Okay. Input and output like this. The state will be there. Output. Yeah. Did you understood? One second. Yeah. Yeah. Next we'll see. Okay. Next. Next FSM More we'll see. Okay. FSM More. What is this FSM More? We'll see. Finite state machine. More. What is this? More machine. We call as More machine. Okay. So More machine. So we can say that the output Output is function of only the present state of the circuit. Output is only the function of present state of the circuit. Okay. So how we can write the Moore machine? Like you have next state combinational logic, next state combinational logic, next state combinational logic, and next you have state register, state register, and next you have output combinational logic, output combinational logic, and here this is input, and the output will be feedback like this. Output will be feedback, and here you have a clock. Here you have a clock and output. This is output Mealy type, Moore type. So output Moore type means what? Is there any connection to the input? So that's why output is depends only on the present state. That means output of the combination circuit. So state register you have a present state, and so present state is nothing but we can say that present state is nothing but previous output. There will be feedback now. After getting the feedback, whatever the output you are getting, that is nothing but we call it the present state. Did you understand this? So coming to the state diagram, how to draw the state diagram? You have one state and next other state, and this is the start state or power on reset, and it is going from one state. So here output is defined within the state itself only. Why? Because output depends on the present state. No, here you are defining the input. Did you understood this? Okay. So here, if you see Mealy versus Moore, Mealy versus Moore, Moore. So Mealy versus Moore. So I will write here Mealy state machine, Mealy state machine, and next one is Moore state machine, Moore state machine, or FSM, finite state machine. Here, if you if you do the differentiation, here output is function of what? Input. Yeah. Here output is function of only present state. Only present state. Yeah. Only present state. Okay. And so coming to, so when input changes, output also changes. No. When input changes, output also changes. Also changes. Okay. Here when input changes, when input that means output does not change. When input changes, output does not change. Output does not change. Okay. Next, number of states is required as the same number of bits. Okay. So we are going to design the sequence detector. Okay. One second. Number of states, number of states required is same as number of bits. Number of bits. Okay. Here one more extra state is required. One more extra state is required. Okay. One second. One more extra state is required. Okay. Required. Okay. And next, it will react to faster inputs. React faster to inputs, and this will react slower to input. slower to input, and there will be one clock cycle later. One clock cycle later. And this one is asynchronous output generation. Asynchronous output generation. And next, this one is synchronous output. Synchronous output generation. Okay, synchronous output and state generation. Synchronous output and state generation. And it is difficult to design. Difficult to design. Next, this is easy to design. Okay. Did you understood the difference between Mealy and More? Okay. Next, we are designing the sequence detector. Sequence detector. Sequence detector is nothing but what? It will accept the string. It will accept the a string of bits. Okay, a string of bits. Okay, it will accept the string of bits, and it will generate the output as one when target is detected. Okay, it will generate the output output as one when target is detected. When target target is detected. Okay. Here in this there are two types are there. One is non-overlapping, another one is overlapping. So non-overlapping means what? Non-overlapping means the final bit of the sequence cannot be the first bit of next sequence. Okay. Here I am writing final bit of sequence. Final bit of sequence cannot be the first bit of the next sequence. Next sequence. Next overlapping. Overlapping. You have the final bit of the sequence. Final bit of the sequence can be the first bit of sequence. Can be the first bit of sequence. Okay. So today we'll discuss Mealy, and next we will discuss More. Okay. So Mealy, if you take, suppose let us take random input. Let us take 0, 1, 1, and 0, 1, 0, 1, 0, 1, 1, 0, 0, 1. Okay. So you need to, like example, you are designing a 101 sequence detector. 101 sequence detector. So that means when 101 is, when you are getting 101, the output should be what? 1. Okay. First, non-overlapping. Non-overlapping, if you see, so non-overlapping. So here, suppose here 0 means what? You are not getting any sequence, no? 101 you are not getting. The output is 0 only. Okay. So this is 0 only. 0, 1, 1, 0 only. And 110, you are not getting the sequence output. 110, output is 0 only, no? What you are checking? 101, no? Yeah. So next 101 means you got the sequence. Output becomes 1. Okay. Output becomes 1. Okay. And next, if it is 010, you didn't got the sequence. So that means here it will start from freshly. Okay. You got the sequence now. So the final bit of the sequence cannot be the first bit of next sequence. So that means freshly it will start. So this is 0, and next 0 1 0, and 0 1 0 0, 1 0 1 again output becomes 1. So you got the sequence. Okay. And after that freshly it will start. 1 means what? 0, 1 0 means 0, 1 0 0 means 0, 001 means what? 0. Oh, yeah. Understood? Yeah. This is nothing but non-overlapping. Okay. So coming to overlapping. So once again, I will write the sequence overlapping. Sorry, first random sequence. First, I am writing the random sequence, input sequence. Let us take input. Okay, I am taking the same input 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1. Okay, so this is overlapping. Overlapping. So if you see the overlapping, yeah, we'll see the overlapping. Yeah. So here 0 means what? Output is 0 only. 0, 1 means output is 0. Again here also 0. 1, 0, 1, 1, 0, 0. 1, 0, 1 you got, no? 1. So this you got the sequence. So this is overlapping means the output of the sequence becomes the first bit of the sequence. Means that will be repeated. The final bit of the sequence can be the first bit of the sequence. So that means 1 will be included. Understood? 1 will be included. So 1, 0 means what? 0, 1, 0, 1. Now it becomes 1. Yeah. Now this 1 will be included. So 1, 0 means what? 0 only. 1, 0, 1, 1 you got. Okay. Again this will be included. 1, 1 means 0 only. And 1, 1, 0, 0 only. Again 1, 0, 0, 0 only. And 0, 0, 1 means what? 0. So this is nothing but overlapping. Did you understood? Okay. Yeah. So next state diagram. Okay. State diagram for the sequence detector. How to draw the state diagram for the sequence detector. Okay. So state diagram for sequence detector. So how to draw the state diagram for sequence detector means first add with the initial state. You need to start with the initial state. Add a state that recognizes the first bit. Suppose if first bit is recognized, it will go to the next state. Okay, and add the state that recognizes the each and successive bits. Each time when you are adding the row, so that means it will go to the previous state or new state. Okay, add the state transition arc which specifies when bit are not in proper sequence. Final state is what? Final state is the input sequence occurs, that is denoted by 1. Okay, so these steps I will tell you, don't worry. So this is 101 is there. Okay, I am detecting this 101 sequence. Okay, first I am designing for Mealy non-overlapping. Mealy non-overlapping. Okay, non-overlapping. So when you design this Mealy non-overlapping, first how many states are there for Mealy? 3 states are there. No? See here in the differences I told you. Number of states required is same number of bits. Here how many number of bits you are using? 3 bits. So how many states you need to use? 3 states. S2, S0, S1 and S2. Did you understand? Okay. So I am drawing here. See here. S0. You are at S0. Okay. So suppose if it is 0. Okay. If it is 0, it will be in same state now, and output is 0. Why? Because you are expecting 1, but you got 0. Okay. You can get either 0 or 1. Here you can get either 0 or 1. So if it is 0, it will be same state. If it is 1 means where it will go? Next state. So 1 and you didn't got the sequence, output is 0. Okay. So here you got the sequence what? 1. Okay. After 1 you can get 1 0 or 1 1, no? You can expect 0 or you can expect 1. Okay. If it is 1, it will be in which state? Same state. It will be in the same state. Why? Because this 0 is the initial state. No. Here 0 you came, but 1 means what? Actually, you are expecting 0, but 1 second. 1 second. Here, if it is 0, if it is 0, it will go to the next state. Why? Because you are expecting what? After that, 0, no? 0, no? So, 1, 0 you got. Okay. So, the input is 0, output is what? 0. Okay. If it is 1 means what? It will be in the same state. Output is 0. Did you understood this? Okay. And next you have 1, 0. You can expect 0 or 1, 0. You can expect 1. Is it fine? So, that means if it is uh, if it is 0, it will go to the initial state. If it will go to the initial state. If it is 1 also, it will go to the initial state, and you got the sequence. Output is what? 1. Did you understood this? 1, 0 and 1, 1. Okay. If it is 0, it will go to the initial state. What is the initial state? 0, no. If it is 1 also, it will go to the initial state. Means non-overlapping means what I told you. Non-overlapping means the final bit of the sequence cannot be the first bit of next sequence. It will start freshly. It will start from the initial state. Did you understood this? Yeah. Okay. Next, suppose I want to draw 101 sequence Mealy overlapping. Okay, 101 sequence Mealy overlapping. So 101 sequence means you are at S naught. So you can expect either 0 or 1. No? If it is 0, it will be in which state? Same state. Okay. If it is 1, it will go to the next state. That is S1. Okay. This is what 1. Okay. So after that you can expect 1 0 or 1 1. No. If it is 1 0, so this is nothing but 1 and output is 0. If it is 0, it will go to the next state. So it will go to S3. Okay. So here you got the sequence 1 0. Next what you are expecting? 1 0 0 and 1 0 1. Okay. So 1 0 0, where it will go? Tell me. 1 0 0. So 1 0 0 means you need to see like anywhere. I need to see 2 bits. 2 bits anywhere 0 0 is there? Not there. I need to see 1 bit. 1 bit 0. Where is 0 is there? Last. So that means this will go to the last state. So this is 0 and output is 0. Okay. And next 101. This is overlapping. You need to check for 2 bits. 2 bits anywhere matching. 0 1 anywhere matching. You need to see this. 1 bit you see anywhere matching. No. So here 1 second. This 1 means same state only. This I missed. 1 by 0. Hmm. If it is 1, tell me the state. Hmm. Here where it is matching, here it is matching now. Overlapping. So it will go to S1. 1 and output is 1. Did you understand this? Okay. So what is the difference between these two? So when one is means when one is getting, it will go to the initial state. But when one is getting, it is go to which state? S1. As this is what overlapping state. Okay, understood? Okay, and next. So I will design for non-overlapping sequence detector. You design for overlapping. Okay. Design. So first we will see the design steps. Design steps. These are common for both Moore and Mealy and Moore. Design steps for sequence detector. Okay, detector. Mealy or Moore. Mealy or Moore. Okay. First, what you need to do? Step one. You need to draw the state diagram. Draw the state diagram. Okay. And next, what you need to do? You need to write the state transition, state table with output. You need to write the state table, state table with output, with the output. Okay. And step three, assign the unique codes for to each state. Assign the unique codes to each state. Okay, each state. Okay. And step four, determine the number of flip flops and type of flip flop. Determine the number of flip flops and type of flip flop. And step 5, write the excitation values for flip flop inputs. Write the excitation values. Excitation values for flip flop inputs. Okay. Find the simplified expression by using K-map. Okay. Find the simplified equation. Simplified equation using K-map. See here, K-map we used till serial adder. Okay. So K-map is very much important. Understood? Each and every design we are using K-map, no? Okay, to get the logic expression, we are writing with the K-map. Draw the logic diagram. Is it fine? Okay, these are the steps. Okay. So next, I will draw this sequence detector. Sequence detector. Mealy, Mealy, non-overlapping. Non-overlapping sequence detector. That too, I am designing for 101. What is that? 101. Okay, 101. First, you need to draw the state diagram. No? What is the first step? State diagram. You need to draw the state diagram. Okay, step one. Step one, you need to draw the state diagram. Okay. So we already drawn the state diagram. That is S naught. Yeah, tell me. It will be in the same state, 0 by 0, and next 1 by 0, and this is S1, and you are at S1. Here you got 1, and if it is 1, it will be in the same state, 1 by 0. If it is 0, it will go to the next state. This is S2. Here you got 1 0, and next uh, so this is 0 by 0, and next for this for 0 by 0 or 1 by 1, it will go to the initial state. Is it fine? Step 2. Step 2. Step 2. What is step 2? You need to write the state table with present state and next state. Okay. So state table, present state and next state. Next state at x equal to 0, next state at x equal to 1, and next present output when x equal to 0 and x equal to 1. Okay, okay. So that means how many states are there? Three states are there, no? Suppose for S naught, tell me the state when input equal to 0. What is the next state? Mm. S naught. Okay. What is the output? Zero only, no? And input equal to one. It will go to oh, S1. What is the output? Zero. Okay. Input equal to S1. What is the output? What is the next state? What is the next state? S2. And output is 0 only. And input equal to 1. S1. Yeah. S1 output is 0. And S3. Both are S0, no? S0. And input equal to 0 means output is 0. Input equal to 1 means output becomes 1. Is it fine? Do you understood? By seeing this diagram only, I wrote the state table. See here, you are at S2. You are at S2. Input equal to 0. What is the next state? S0. And input equal to 1. What is the next state? S0 only. S0 only. And what are the outputs? 0 and 1. No? Do you understood? Okay. And step 3. What is step 3? You need to give the unique codes to each state. Let us take, I am giving S0 equal to 0 0 and S1 equal to 0 1 and S2 equal to 1 0. You need to give the unique codes. Okay. And so by using these unique codes, you need to draw the state assignment table. What is this? State assignment table. State assignment table. So what is state assignment table? Present state and next state and input x equal to 0, x equal to 1 and next present output x equal to 0 and x equal to 1. Okay. So here 0 0 S naught means what? 0 0. S1 is 0 1 and outputs are 0 0. Okay. 0 1 1 0 0 1 0 1 and S2 1 0 0 0 0 0 0 1. Okay. So after that you need to draw the so this is fine no state assignment table. Okay. Simply like wherever the S naught is there, you need to replace 0 0. S1 is there 0 1. S2 is there 1 0. Okay. So once again I am writing state assignment table. Why? Because by seeing this only I need to draw the detailed state assignment table. Okay. State assignment table. So state assignment table. Uh, so present state and next state for x equal to 0 and x equal to 1 and next you have present output x equal to 0 and x equal to 1. Okay. So you have 0 0 0 1 1 0 1 0. So this is 0 0. Okay. This is 0 1 and this is 1 0 and 0 1. Both are 0 0 only. Here all are 0 only. Here last output you will get 1. Okay. And next by seeing this you need to draw the detailed state assignment table. Detailed state assignment table. Detailed state assignment table. How to draw the detailed state assignment table here? Uh, so let us take present state. Present state are nothing but Q1, Q0, okay, and input is what? X, okay, and next state Q1 plus and Q0 plus, okay, and next you have flip flop inputs, okay. Select the type of flip flop means I am using D flip flop. Number of flip flops means you need how many flip flops? Two flip flops. Number of flip flops means you need to require Q0, Q1, Q0. No, how many flip flops are there? Two flip flops. No? So this is D1 and D0. These are the excitation values and output Y. Output Y. Okay. Okay. See here. So three inputs are there. How many possible combinations? 8. No. 8. So 0, 0, 0, 0, 0, 1, 0, 1, 0, and 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Yeah. So see here, just I am dividing. Now you see. So present state is 0, 0. What is the next state for input 0? 0, 0, no? 0, 0. Present state is 0, 0. For input x equal to 1. What is the next state? 0, 1. Okay. Present state is 0, 1. For input x equal to 0. What is the next state? 1, 0. Present state is 0, 1. For input x equal to 1. What is the next state? 0, 1. Present state is 1, 0. For input x equal to 0. What is the next state? 0, 0. Present state is 1, 0. For input x equal to 1. What is the next state? 0, 0. Okay. This we are not using means don't care. Sorry. Okay. Did you seen the excitation table for D flip flop? Qn plus 1. Did you remember the excitation table? 0, 0, 0, 1, 1, 0, 1, 1. There I said no. Whatever the Qn plus 1 is there, that will you come into D, no. Did you remember? Did did you remember that excitation table? So here simply that is the beauty of D flip flop. Whatever the next state values are there, directly you can write. No need to remember. Okay, this is 0, 0, 1, 0, 0, 0. Don't care, don't care. And what is this? 0, 1, don't care, don't care. What are the outputs? Tell me. 0, 0, and 0, 0, 0, 1, and this is don't care. Don't care, don't care. Yeah. So this one not required. Excitation table. Is it required? You remembered, no? Oh, okay, okay, okay. So here you see what is D1? Tell me. D1 in terms of Q1, Q0, X. Tell me the midterms. Tell me the midterms. 2, 2, no. D1 equal to 2. 2 plus don't cares of 6 comma 7. No? 6 comma 7. Okay. And next D2 D not equal to what? 1 1 comma 3 plus don't cares of 6 or 7. Okay. Y equal to summation of m of phi plus. Okay. Can you draw the K map and get the logic expression? Draw the K map. I'll give 5 minutes of time. What happened? Hmm. What is D1, D0, and why? Hmm. How you are getting that? What are the inputs? Q1, Q0, X. 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 2, 3, 4, 5, 6, 7. 2, 6, 7. Yeah, you can consider this don't care as one means this is pair no. So this is pair means I will consider this as zero. Why you need one more prime implicant? Not required no. Q naught X bar. Q naught X bar. Okay. Next D naught Q1 Q naught X 0 1 0 0 0 1 1 0 1 1 0 1 2 3 next 4 5 6 7. What are the minterms? 1 3 6 7. 1 3 6 6 7. Yeah. 1 3 6 7. This is one pair no. What is this? Q1 bar X. Q1 bar X. Q1 bar X. Okay. Q1 bar X is common no. Okay. X is common. Next, the other came for Y. What are the inputs? Q1 Q naught X 0 1 0 0 0 1 1 0 1 1 0 1 2 3 4 5 6 7. What are the minterms? 5 6 7. 5 6 7. This is one pair no. What is this? Q1X no. Q1X. Q1X. Okay. Now I will draw the circuit diagram. So I'll consider this as zero. Why you need extra prime implicant? With this pair is completed, no? I will consider this as zero only. I don't need a circuit. We should be like minimize the minimum number of literals. It should be minimized. Minimum, that means he should have the minimum number of prime implicants. Okay, okay. So here I am drawing the diagram. Yeah, separately I will draw. Okay. Yeah. So what is D1? D1, D naught, Q1 bar X, X, Q1 bar X, and D Y, Y. Okay. Y is what? Q1X. Yeah. Q1X. Q1X. Okay. So you need to use 2D flip flops. This is one flip flop D naught, Q naught, D1, Q1. Okay. And you are giving the common clock. Let us take passage of clock. This is common clock is given. Here this is clock. And here one input is X. So next Q1, Q naught, D naught equal to what? Q1 bar X. D1 equal to D1 equal to Q naught X bar and Q1 bar X. Okay. So here D naught equal to what? Q naught X bar. Okay. Q naught X bar. Okay. D1 equal to. So this is Q naught, and here this input is coming like this, and this it is coming through the inverter. This is X bar. Okay. So let us take this is one X input. So this is given to one AND gate. This is nothing but D1. Okay. And D naught equal to what? Uh, Q naught X, Q1 bar. Q1 bar X means you need to take the input from here. You need to take the input from here, and one input is X only, and this is given to D naught, and this is Q1 bar. So X Q1 bar. Okay, this is Q naught X bar. Okay, and next what is Y? Q1X. You take from here, and this is output Y. Okay, output Y. So this is Q1X. So from this, you can identify is this a Mealy machine or Muri machine? Why? Because output output you are getting from the input, present input, and output of the flip flop. That is nothing but present state. Did you understand? Okay. So this is about the finite state machine designing and designing of sequence detector for Mealy machine, overlapping, non-overlapping, and designing of sequence detector 101 sequence by using for non-overlapping sequence. Same thing you need to try for overlapping sequence. That is your task. Hmm? Understood? Okay.